Good morning, everybody. My name is Chris Conway. I'm the president of Conway Energy. I'm a roamer, so you're going to see me do that probably quite a bit. I'm not trying to dance, but um, I'm in the Northern Virginia area. I serve Northern Virginia, DC, and Maryland. Basically, we specialize in high performance homes, multifamily, single family, and now light commercial we're getting into. So I'm going to actually get right in it. So thank you all for joining us, both near and far. We know you're all are very busy, very important people, and glad you can come out and join us today. And those on the webinar, thank you for taking time out of your day. I'm going to come right out and say it. We have, as an industry, need to be better at designing, installing, commissioning our HVAC systems, heating, ventilation, and air conditioning. We figured out how to do building envelopes pretty well. And they are tighter, they're better insulated, they're more resistant to Mother Nature than ever before, but obviously no good deed ever goes unpunished. And as we've gotten better with our envelopes, we have created kind of new problems. Very easy problems to understand that we've created, but it's kind of taken a few minutes for the industry to kind of really grab on and accept those new problems. We've changed the way our buildings operate. And if you can imagine, if we used to live in a basket, we lived one way. And now that we're living in Yeti coolers or those fancy Walmart coolers, we got to live in a little different way. I mean, we're just flat out holding more moisture than we used to. That's just a basic fact. So for some reason, our mechanical systems have struggled to adapt. We continue kind of the old rule of thumbs, the old practices, and unfortunately, some of those old rules and old practices are kind of creating a harmful environment, health environment for both our buildings and our occupants. And that's ultimately why we build buildings, is so occupants can be in them. I personally know that buildings without occupants operate fantastically. Never a problem. But as soon as we get in there, boy, we really muck it up. So when you're thinking of mechanical systems, it's very important to consider them as kind of a permanent fixture of the house, as permanent as your structural members. Because once that drywall is hung, that's it. You have no chance to get it right again. So the only way you're going to know if you kind of got it right later is if you're having moisture problems or structural problems because of moisture problems, or you got very uncomfortable occupants. And so to fix both of those things, it's very costly. So why we only put 3 to 5% of our entire house budget into the entire comfort making mechanism is amazing. We used to spend almost 20%. But we've kind of shrunk that down a little bit, and that's a little unfortunate because that's the thing that we use to stay comfortable and dry. So, for all you kind of multifamily types, how satisfying would it be to get it done right the first time? And every update and renovation that you do from that point forward, you don't have to worry about controlling moisture, making sure there are no hot and cold spots. All you got to do is swap out to the new latest and greatest heat pump or air conditioner or furnace and move on. You just lipstick and paint and make the building better. So a lot of my renovations now involve fixing ductwork, fixing mold problems, fixing things like that have crept up over the years. So it'd be great not to have to worry about that. Just think about the savings that we would have. So it can be argued that the incorporation of air conditioning in buildings is probably one of the single greatest achievements, building advancements in the modern era. At least for me in the summertime, like today is ridiculous. I need my air conditioning. But originally, air conditioning had nothing to do with keeping people comfortable. It had everything to do with keeping factories comfortable so we didn't ruin all the stuffing. So clothing manufacturers, things like that, they didn't want to ruin all their clothing in there. eventually we came about that, well, we as people like to be comfortable too. And that kind of migrated through the Southeast, as you might imagine. But uh, it can also be, air conditioning can also be argued that is one of the greatest misunderstood and sources of problems in a building, because we just started doing them wrong. And now that we're changing our buildings again, we continue to kind of do it wrong. So what is air conditioning? And it's important distinction with air conditioning, because it's not air cooling, right? So we're not just cooling the air. Conditioning, in its truest sense, is cooling, drying, filtering the contaminants in the air, ventilating or bringing fresh air in from the outside, and then potentially distributing, most importantly, distributing that nice conditioned air throughout the house, throughout the space. Um, that's when everything, if all those things align, then we have a great comfort system and no problems. We've done an excellent job at progressing the cooling piece of the condition puzzle, but unfortunately, we have basically fallen short in about every category. Um, where is the mouse? Well, I want to. Technical people, technical. Here we go. I will actually come back to the slide, but all right. So we've done an excellent job. So let's do a little bit of an air conditioning status check of where we're at. So cooling, we get a star. We're doing a good job. We can make stuff colder than it used to be, so that's good. Filtering, not so much. Basically we're still using filters that catch dogs and cats and small chairs and things like that. We don't really do a good job at taking out the contaminants in the system to, be a little better of air for us to breathe. Ventilation, boy, we're still screwing that up. It's a hodgepodge of ineffective, kind of uncontrolled strategies. We still like to argue left, right, and center why we can't have exhaust-only strategies. If I'm in San Diego, exhaust-only is fantastic. But in this climate today, I don't want to be sucking this air that's outside of our window right now straight into our house through every cavity, nook, and cranny in the joint. So, and then the implementation and distribution of has become kind of fodder for many pictures on the internet of great installs. We got to install these things right. That's a little silly. Energy Vanguard has actually printed here before, Allison Bales, so I credit him for that slide because it's his. And in drying, we've really done a bad job at drying, right? So we're going to get into today. That's what this is all about today, is about the drying. So, probably the most detrimental is this drying. We've exaggerated the capabilities of an air conditioner's ability to dry. So an air conditioner's ability to dry is basically just an accidental side effect of cooling. And now it may work in some conditions, but it does not work in all conditions. And it only works when the thing is running. So on a day like today, when it's 73 degrees outside, if you set it at 72, it's probably not going to run very much. But as those who walked in this door know, it's very humid, and that air is coming into our house and just loading up the house. So unless you want to hyper cool the house, you're never going to dry anything. So, so today, with my expert colleagues that you see over there, we're going to focus on kind of getting a better handle of handling the latent load, or basically drying the high performance buildings. We're going to demonstrate some cool air and moisture effects with this ham house. We're going to talk about the importance of sizing and selecting an air conditioner to fit your high performance house building, and then the necessity of adding dehumidification systems to basically all mechanical systems, especially in hot, humid climate regions or warm, humid climate regions. So I think because we have to, I got to show stuff like this.
Go right through.
All right, there we go. This is AIA. Everybody, mark your calendars. You're getting stuff right now. We're going to learn some things. You read all that, and that's why you signed up. You thought it was so great. All right, there's our status check. What is a high performance home? Here we go. Basically, we're going to kind of scroll through this here a little bit. It's one that's basically comfortable, healthier, more resilient, more durable, and if you add all that stuff up, it's more energy efficient, right? I mean, we've been saying what a high performance building is forever, and every time we say we're uncomfortable, that's probably an indication that it's not really a high performing building. So, without going on a soapbox of high performance building, that's generally what we're looking for. So, in the interest of time, we are going to move on to the Ham House. This is the Ham House. It was created by Anthony Cox, the building science manager, lead trainer at CHP, one of my most favorite people in the world. He's a weatherization guru, and they got a fantastic training facility down there in Christiansburg. And if you go down there, he'll probably take you out to some barbecue. So make sure you see Anthony down there. So the Ham House is used to demonstrate basically some physics things. We're going to talk about two elements of a high performance building: a little bit of air sealing, have nice tight envelope, and a little bit of insulation. So I'm going to try to demonstrate in a few minutes of kind of effects of good insulation or good air sealing or not, where to air seal, some certain pressure differences. I am going to be slightly handicapped because I'm sitting here in front of the computer, but we'll do what we can. There is a house. Oh, I got a picture. I got a picture. So don't worry. Hold on. We're getting there. Webinar people, I will have a picture momentarily. So a little bit of physics, a little bit of thermodynamics. Hot goes to cold, right? Wet goes to dry, high to low. Basically everything's downhill, right? High to low, wet to dry. When you use your grandma's quicker picker upper and you put it in the sink, it doesn't get drier, it gets wetter. That's what happens. So, and that's just the same general thermodynamics. You know, you can't argue these. It's science, right? You can't argue science. You just kind of live it. What we got to understand is that that we need to work with these factors. We need to understand them. It's not rocket science. Basically, if it's hot outside, it wants to come inside. If it's hot inside, it wants to go outside. That's it. That's it. You're just driving forces one back. And the house is constantly trying to regulate. Your house, whatever you're in, your structure, your building is just an environmental separator, right? You're trying to just be nice and dry and warm and healthy air, trying to keep it outside of this, whatever air we're breathing outside, uncomfortable air. So there it is. There's a house for all you webinar people. And that's Anthony Cox. So I'm going to have to do my best at simulating. He always has it a little bit to the right, and I think Anthony would appreciate this a little bit. So so that is the Ham House, everybody. That's what I'm going to be working with. I'm going to show a little bit of air sealing, the importance of it, and then we're going to have a little bit of moisture demonstration. So the Ham House is known as the House of Amazing Meat. So we'll put meat in here and we'll cook on it, and it's tasty. But no, it's actually the House of Air and Moisture, and that's heat, air, and moisture. Ham House. So there you go. So it's Anthony has created a number of houses. The old House of Pressure used to be his big one. Now this one is. So this is that's good. It's great to have it here. Anyway, let's get right to it. So we got the stack effect. Basically, stack effect, without arguing with all the more physics types, basically hot air goes to cold air. So in the winter time, basically heat rises or heat goes towards the cold. That's what we're doing. And in the summertime, when you got hot upstairs into the attic, it goes to the cold, comes down, right? So let me show you a few things. So right now I've heated this house up to, well, anybody tell me? 145 degrees. All right, 145 degrees this house has been heated up to. Now all this is trying to do is simulate kind of how a house is operating in the wintertime. So basically it's warm inside, but not really and colder outside. So, all right, let's talk about some air sealing. So the best thing the way to look at this is you got to crawl. First floor, second floor, third floor. This could be a house. This could be a multifamily building with one apartment over another. But basically, all it's trying to show is just a tall building that's been air sealed or separated amongst the two. So, but in this demonstration, it's going to be just like grandma's house, hanging out in here. So what we're going to do first is right now, there is no ability for air. It's been air sealed from the crawl space, and there's no way to connect from the house to the attic. All right, so if I blow in some air here, this is where things are going to get tricky, everybody. So I have this little folder, indoor air pollution. If I blow air into here, tell me if you can see this from there.
We have a couple folks from Arlington County.
Probably not, since the stick doesn't work. Gotten clogged. I might need that. Where was he? I might need that one. Yeah, it looks like it's been plugged. What else can we do? Anybody got an idea? Stand by.
Got that screwdriver pen? The handy dandy. Oh, yeah.
All right, stand by on the webinar.
Yeah. That ain't happening. That ain't happening.
No.
Let's see.
Oh, I might just have to.
All right. Well, there's nothing. Oh, hey, I got it. Let's turn this on.
There you go.
Hey, we got something else. All right, we're back on. Sorry, everybody, for the technical difficulties. It looks a lot better in person, I bet. So what I can't see from the back. So what I've done is there is a smoke generating machine in the crawl that's kind of signifying contaminants and things like that. I'm going to have to turn this so I can see something. But basically, there is a bit of a stack effect. So can you all kind of see some of that air smoke coming up, right? So all I've done was create a little bit of connection between the crawl and the house. That's it, okay? And so it's not so bad. It's not so bad. It's like your radon is just hanging out, you know, all your nasty, right? It's not bad. It's just the first floor people. So we got that, but what happens if we don't air seal our attic? Does anything happen? Do we? What? Did that work? Do you see air moving? So what's happening is there is a connection from this crawl all the way to the attic via stack effect. So there is a positive pressure up top, which this hose is showing, and there is a negative pressure down low. So air is coming in from the space, the contaminants into the crawl, and it's being, through stack effect, it's rising through the house. You guys see that? So if you were going to start to air seal something, or just argue, can you see it up here? Or just argue, why are we air sealing buildings? I don't know if you can see that or not. But why you air seal buildings is so you're not creating a constant flow of contaminants, outside air, hot air, cold air, outside contaminants, and radon. What else is a good one? That's about it. And so anyway, so you start by closing this off, right? So you don't get the pull so much. And then you go and you seal off your crawl space. So that's why it's so important here that we do our crawl spaces correctly so that we're not pulling in the stuff that we don't want to breathe, because we have holes all over the house. And we have to pay attention to that during construction or building during construction, because if we don't, you're going to get the free movement of air coming through, and that air is full of nasty stuff. I wanted to show you a nice big old puffer, but obviously that didn't work. So the next thing is a little bit of moisture. So I'm going to pour some water in here real quick. Anything you want to add, Nikki? Rob, while I play with water? Well,
No. Well, we actually,
yeah, you got to be over here.
the question was, is there a resource on how to seal crawl spaces? I would say Advanced Energy in North Carolina is probably the leading organization. We actually worked with them to develop a 2-day class about the building science of crawl spaces. And it's not promoting dehumidifiers. It's basically, as a crawl space contractor, you need to know the building science before you just start going in and putting vapor barrier and sealing up vents, because you could be doing more harm. Actually, North Carolina is just taking it on as their credentialing program. And they're doing a class November 8th and 9th in Raleigh. And we worked with Advanced Energy to get the how-to and all that. But if anybody wants any more information on that, but I would say Advanced Energy for sure is probably the leading organization on crawl spaces.
I think so. Yeah. So, all right. So I added. So for those on the webinar, you're missing a very sweet demonstration. What I've done is I actually put some water in some kind of butter warmers in the ham house, and it's going to simulate a moisture. It's going to simulate a kind of a moisture generation source. So you come home after work and you start making dinner and take a shower and all that kind of good stuff. People breathing and all that. So you're creating moisture in a house. But now this house is basically a tight house, right? It's more of a high performance house. So I just really quickly went through what a kind of a nice air seal envelope is, right? We kind of close off the top and bottom, and then all of our windows are closed. But now we got a little bit of water in there. So let's talk about relative humidity.
I can't video it because
Basically, relative humidity is the amount of moisture at a given, the amount of air that the water occupies changes with temperature. Wow, I don't like that. I don't like that. So humidity is relative to the temperature. So if you have this filled up with water, right? If this is filled up with water and say this is 50 degrees, right? 85% of it filled with water. Follow? You go and then you take it and you pour that same amount of water into this other container that I have. What it's going to do is it's the same amount of water, but it relative to the overall size, it's less. So your relative humidity goes down, right? Makes sense? So it's the same amount of water, but kind of a bigger container. And then if I were to pour this water into this ham house, it's going to be the same amount of water,
well, I only
less relative to the overall container. Does that make sense? So that's basically what that slide's trying to show, that relative humidity can change, even though the water quantity is the same, that it will change based on how hot or cold the air is. So the warmer the air, the more moisture that it can hold. Colder the air, the less that it can hold. The best way I think about it is when you're cold, you're kind of all huddled up together, and there's not a lot of space for moisture to get between you. But when it's warmed up, you're dancing, you're having a good time at the party. There's a lot of space between you to fill up with moisture. So not very scientific, but that's the way I think about it. Anything you want to add, Nikki? No? How temperature impacts the RH. So for each 1 degree of temperature increase, the relative humidity goes down, right? So just like I said, so when you start adding the temperature differences, your humidity goes down. The amount of water in the air doesn't change, but how it is relative to your temperature changes. And then kind of inversely, for each 1 degree the temperature decreases, the relative humidity increases 2%. So, you know, it's pretty interesting to see that you're going to have some changes in relative humidity. So in the wintertime, you could be sitting in your crawl and it's 30 degrees outside, but you got like 90% humidity. But that's hardly any moisture at all because there's not much moisture in that air. So that's why we get all chapped up and chapped lips galore and everything's drying on our skin and everything like that in the winter because there's just no moisture in the air. That's it. So, all right, dew point, here we go. I'm coming up towards the end of my show. So if this thing heats up fast enough, what I wanted to show was dew point and basically condensation. So there is water in those butter warmers. And as it heats up, it's going to condense basically at dew point. So it's when this water cup that we talked about gets filled with water all the way up to 100%, which is dew point, and it starts to come over. When it starts to come over, that's basically your condensation. You have too much water. The space cannot hold the amount of water you have, so it's trying to get rid of it, right? It's trying to get rid of that vapor. So it condenses to bulk water, and then all of a sudden you see it on your windows, you see it everywhere. It starts to condense. So we might have some in there. Do you guys see any condensation in there on some of those windows? Do you see anything? For those that can't see me, I'm actually behind the ham house, so I can't really see what's going on. You guys see that? All right, so the garter belt that was holding this insulation is representative of keeping this surface warmer, right? So when this water warmed up and was condensing on the cold plexiglass, this insulation was keeping it warmer, and it was basically preventing the condensation from happening to begin with. So when you're building houses, one of the great things to always do in this climate region, or one of the game changers, is to have continuous insulation on the outside. We can go into a number of reasons why otherwise, but you know, it's more than just thermal. It's stopping condensation. So this is happening in your house all the time. In the wintertime, condensation is forming on all your building materials constantly. And so if you have that on there, much less of the ability for that to happen. Okay? So that's just a quick demonstration. So condensation, once again, when the dew point is above the surface temperature, then condensation will occur. If it's below, then there will be no condensation. So who knows? We'll see. You can see it all fogging up now, and it'll start to grow and fog all the way up, and you'll start to see that there's a lot of condensation behind here. So
I think
yeah. So anything colder than 75 degrees today is going to condensate. So if your ducts are 55 degrees in your house, your ducts could be condensating if you don't have a nice air barrier on that outside, and that warm, moist air can touch that ductwork. That makes sense. So anything colder than 75 will be condensating at some point. It's okay for buildings to get wet. It's okay for components to get wet. What's not okay is that they don't dry. Drying potential is everything. We need to be able to dry. And you have to have 3 times more drying potential than you do wetting potential. So the problem is not wetting. The problem is lack of drying. Okay? So we've been getting wet for a long time. All right, here we go. I'm about to wrap this thing up. So to kind of get into the presentations that are coming, we need to know a little bit about sensible and latent load. Sensible, all that you want to, the best way to think about it is sensible is what you feel. It's the temperature that you feel. But perhaps most importantly and most applicable to this conversation is that's what your thermostat measures. Your thermostat's on that wall measuring temperature. It's measuring sensible. What it's not measuring is the other component of heat, and that's the latent load. basically that's the amount of moisture in the air, that relative humidity that we discussed. And that is not being what's measured. So you could have a kind of a cool house, so your sensible is low, like 70 degrees, but you can have a high relative humidity. You could have 70 RH, and that's not good. So what we need to work on is working on, and we're going to discuss it through the presentation, is driving down that latent. Because if we can drive down the latent, we can get rid of the moisture from the system, and we'll have a much more comfortable house. So high performance homes, this is what we've done, right? This is it. High performance homes is basically low sensible load home. We've added insulation, we made it airtight, we've optimized our windows and shading, we've put in mechanical ventilation, and our ducts are in conditioned space. All those things, if we don't do that, contributes heat to the house. And if it's contributing heat to the house, it's going to make your air conditioner run more. Does that make sense? So all of a sudden we make our basket into a Yeti cooler. There's no heat coming in there, so the air conditioner never runs. Okay? But on our latent side, with our new high performance homes, our airtight construction is decreasing the amount of moisture coming in because you don't have all the air leaks anymore, right? So you don't have as much air leaks. But what's happening is we're pumping in air from the outside for mechanical ventilation. So we're driving up mechanically the amount of moisture in the air. And then on top of all that, you add occupants. So we're decreasing the amount of heat that's coming in the house, but we're increasing the amount of moisture that comes in, and we're adding people to the space, or now the effects of people in the space are much greater, right? So as you can see here, one person adds a quarter pint of moisture from breathing, plus a quarter pint from activities in a home in an hour. That's actually a lot of moisture. If you have a 4-person home and a dog sitting running around, that is a lot of moisture coming in the house in an hour. So today, that's what we're going to be getting into. We're going to be trying to drive down. We're going to be trying to hit the point home that we need to right size our equipment to address the latent loads. And ultimately, in this climate specifically, green grass climates, we're going to need to add some dehumidification to kind of close that gap. So. Okay, so there is going to be a phrase between us 3 speakers that is created by 1 word per speaker. So my word is drink. And then now you got to wait for Nikki and Rob to give you the other words.
Okay, so just to summarize to this point, I think it's safe to say if we just stop showering, stop cooking, stop cleaning, I'm good with all 3 of those. I'm not sure about stop breathing. I think I'd like to keep doing that, but I haven't started yoga yet, so I think I'm pretty safe right now. Okay, so if I don't go ahead and give my keyword now, I'm going to forget to do it. So I'm just going to go ahead and get that out there. My keyword is your. Y-O-U-R. Your. None of you people on the webinar. All right, so again, Rob Howard with Mitsubishi Electric Cooling and Heating. So I'm going to dive more into the heating and cooling portion of the presentation. Sure.
Sorry again for the webinar, folks. I don't know if you heard us to start because the audio was bad. That phrase you keep hearing about, at the end you'll be asked to give us the phrase back, and that's what makes you eligible for your AIA credit. So you've heard the first 2. Rob just gave his as your. So just, yes, make sure you're paying attention to that. Thanks.
This is so fun. Okay, so Chris has already spent quite a bit of time talking about loads, but I'm just going to drill down into this a little bit more for you. So it is really important for us to understand mechanical loads on these buildings that we're designing and building. So Anybody know what the old rule of thumb has been in terms of square feet per ton of HVAC equipment? 600 square feet per ton? Do I hear 500? Yeah. So there's all these rules of thumb out there in the industry, right? And I would say at this point in the evolution of our construction industry, none of them work anymore. So let's just abandon those right now. What we're seeing now in these high performance buildings, or what Chris described as low load buildings, is more like 1,000 to 2,000 square feet per ton. So if you're still using the old 4 to 5 to 600 square feet per ton, is that going to be a problem? That's what we're gonna dive into in this next section. So I think it's also safe to say that we've reached a tipping point in the industry where our homes, our buildings are so tight that ventilation is no longer a good idea or just a best practice. It's a requirement. So you just need to decide how you're going to do it and what makes the most sense in your climate zone. But ventilation is absolutely critical if we're going to continue to breathe and do those other things that we like to do in our homes. So you're getting into sensible heat ratios, so I'm not going to spend a lot of time on that. But sensible heat ratios are certainly an issue that we're looking at in the HVAC industry from the manufacturer perspective, because we are going to have to start optimizing for more latent removal, and Nikki's going to cover that in her section. And then, as Chris mentioned, another challenge that we're facing is air distribution. It can also be an issue, so trying to make sure that you're comfortable in all parts of your home. I always like to ask, does anybody have a part of their home that is not as particularly comfortable as they would like it to be? A couple of you out there. Anybody want to throw out an example? What room are you thinking of? A basement bedroom. Man, that might be yeah. That's a whole different kind of man cave, right? Yeah, so a basement bedroom. Yeah, those are challenging for sure. Basements in general, I think, are challenging. But yeah, if you're gonna try to live in the cave, that does make it even more challenging. So, yeah, that's a good one. So you don't see the photo credit here, but I will give credit to Allison Bales from Energy Vanguard for this one as well. So I stole this right off of his blog. But do we have a problem with oversized HVAC in the industry? Maybe it's not this bad, but it's bad. So what's the big deal? What's the problem if we oversize our HVAC equipment? Satisfies the thermostat too fast. So what does that mean? Why is that bad? Short cycles. There you go. And you said, Brian, there's not enough dehumidification, if any at all. That's right. So yeah. All right. You get this. So one of the things that I advocate for when I go out and do contractor and builder and architect training is that we need to move the residential side of our industry along to make it more closely mirror the commercial side. In the commercial world, how many of you guys do commercial work? Not many. So everybody else is residential? Okay. So in the commercial world, you typically have an architect, at the beginning of the project. Then we get the MEP involved. So now you've got a mechanical engineer who's designing the HVAC system, and probably going all the way to specifying the actual equipment that's needed to satisfy the loads in that building. But unfortunately, in the residential process, it doesn't always work that way. You may not have an architect involved. You almost never have a mechanical engineer involved unless it's a really big project, maybe in multifamily, but probably not in single family. Who typically is doing the mechanical design for a residential project? That guy right there. Yeah, Brian is one of our contractors in the room. So he's actually doing load calculations, which is what we're going to talk about next. So typically this falls to the installing contractor in the residential world. So just to make sure everybody's on the same page with what that residential HVAC design process involves. Is everybody familiar with ACA, Air Conditioning Contractors of America? They have a series of manuals that they've created to help contractors appropriately size and design these systems. So just to quickly run through these, Manual J is your basically determining what the heating and cooling loads are on that building. Manual S is where you do your equipment selection. Manual D, if you have a ducted HVAC system, which we often do, that's designing your ductwork. Manual T is for your terminals or registers. There's actually a whole manual on how to size and select those. And I'm always advocating that maybe we're missing one. You know, if ACA's on the line, I would like for you to develop a ductless heat pump manual, because that's where my part of the industry, you know, we're certainly advocating for the use of these products, but there's still a lot of uncertainty, I suppose, on the part of contractors in how to size and specify these properly. We have created some tools to help our contractors do this. This is a report from our Diamond System Builder software. So once you've got your load calculation, you know how many BTUs of heating and cooling you're going to need for that building. You can actually do your equipment selection, you know, the Manual S portion in our software. So this is, well, you don't see all the menus. This is just an output report. You can literally drag and drop equipment into this, so it makes it really easy. And once you've built your system, you can see in the blue number is your cooling and the red number is your heating capacity of that equipment. And that's actually in the specific location where that project is being built. So what's the process involved in actually running a load calculation? What is Brian up to every day? So, you know, we're going to talk, you know, just really break it down to the, you know, the very basic level here. So it's essentially a heat loss or heat gain calculation that's performed to determine the correct size equipment that's necessary for that building. We're certainly looking at what's going on all year long. So as the seasons change, summer to winter, we only have 2 seasons now, so we only have to worry about 2. That makes our job a little easier. But certainly we're talking heat gain in the summertime and heat loss in the wintertime. And we're looking at every aspect of the building envelope. So floors, we're looking at the roof and the ceiling. We're looking at the walls. Is this working? There we go. The windows, doors, the lighting, the appliances, certainly the geographic location of the building, and that building's orientation to the sun. How does the sun impact that building as it moves across it during the day? And oh yeah, those people that we're designing this building for, the ones who are mucking it up, I believe was the term Chris used. I'm one of those, by the way. I have a tendency to muck it up at my house. My wife will attest to that. So if we're actually designing this building for a specific family or business, and we know how many occupants are actually going to be in that building, we can really start to dial into the exact load that we expect. If we don't know who we're designing it for, I'm going to pick on Brian a little bit more here. How do we guess how many people are going to be in that home? There you go. So 1 occupant per bedroom plus 1, assuming that there's going to be 2 people in the master bedroom. Exactly. So just to really oversimplify it, I'm going to say there's 2 kinds of load calculations. One is what we call a block load, where we're just going to pretend like it's one open room. Let's just pretend like this room that we're in is a house, and it's got no interior walls. There's no partitions whatsoever. It's just one big room. So now all we've got to look at is these exterior walls, this ceiling, this floor. That's going to be our load for this building. But most of our homes aren't, you know, we like open concept, right? But not quite this open. We're going to probably put some interior walls in there so we have some privacy for sleeping and, you know, bathing and things like that. So in order to really dial into what load each room has, we're going to need what we call a room by room load calculation. So I would say that if you're not getting a room by room load calculation, you're probably not getting it right. So that's the level of detail that we need. We need to know exactly what the load is in each of these spaces. So, again, my part of the HVAC industry is we're focusing on VRF equipment. Anybody know what VRF stands for? Brian's not allowed to answer. Variable refrigerant flow. Excellent. Yep. So you will most often hear VRF used in our commercial equipment, which is called City Multi. But when our mechanical engineers aren't listening, I will sometimes use that to describe our residential equipment as well. Hopefully they're not on the line either. So why would you want to use variable refrigerant flow equipment in high performance homes? So here's a couple of suggestions. One is you're going to get smaller capacities that match smaller loads. So that's certainly one of the reasons that we want a room by room load calculation. Is I want to know exactly how many BTUs of heat I need in that room in the wintertime. And now I can start to essentially carve that house up into zones. So that's what we're trying to create is smaller comfort zones within the home. And then fortunately, we have smaller capacity equipment that can be matched to those smaller loads in each zone. And if you do it this way, you should see somewhere on the order of 30 to 60% energy savings. So that's a big deal, whether it's a residential or a commercial project. We're also advocating for reducing the amount of ductwork that's necessary to keep that house comfortable in all of those zones. So in fact, I would say my stated goal is to get rid of ductwork. In fact, I recently pronounced that ductwork is dead. That's out there. That's out there on the internet somewhere you can find it. So that's probably not true, by the way. I had a vision for the future where ductwork is dead. So I don't know how long it's going to take us to get there. We tend to be a little slow to change, particularly slow to change in this industry. So, but let's try to limit the amount of ductwork. So maybe we don't go all ductless, but we use less duct. Is often the way I would describe it. So, and the reason for that is ductwork tends to haul around some pretty dirty air, which leads to poor indoor air quality. There are companies out there who offer duct cleaning. There may be some in the room or on the webinar. So, just saying, duct cleaning can be a challenging thing. That's not easily done, especially depending on what material that ductwork is made of. So. So I'll jump down off that soapbox now. But we are also, again, looking at trying to create smaller comfort zones so that we can customize our comfort in each of those spaces. The reality is, as the sun moves across that house during the day, the loads change depending on the occupancy patterns of that building. Your need for capacity in those different rooms changes. So the smaller we can carve these zones up, the more comfortable we can keep people in those separate zones. You also don't have to fight over what the number should be on the magic box that we call a thermostat out there on the wall. I'm sure you don't have those problems at your house. I now have the Wi-Fi thermostat, so I can mess with it even when I'm on the road. So that's fun. Just in terms of getting everybody on the same page of what the VRF system components look like, I'll kind of walk you through this. The units down here on the bottom are the outdoor units. Sometimes you'll hear those referred to as the condenser. And then you have a variety of different indoor unit types. The little black lines are meant to symbolize the line sets. So that's your refrigerant line, your communication line, and we're going to try to get refrigerant to the indoor units. We need to be able to get power and communication to those units, and then we also have to be able to get condensate out of the indoor units to the outdoors. Hopefully we're getting some condensate out of that drain, right? So we'll talk more about that later. So, but you do get to see some examples of the varieties of different ductless units. So, the one on the left there, kind of in the center of the screen, is what sort of the traditional ductless heat pump, sometimes referred to as a mini split. That's a pretty typical unit. But we also have other options, some slim ducted or horizontal ducted units. Again, these are meant to serve smaller zones, not really designed to serve an entire house with one of these, but you can put a little bit of ductwork on these just to serve a master suite, for example. Up toward the top right there, you've got some 2x2 ceiling cassettes, which were designed to go originally in a 2x2 grid ceiling like this, but we do see contractors put those in hard ceilings as well. The only issue there is you do have to have service access either from above, like in an attic, or an access panel to service those. And then you've got a what's called a floor mount unit on the very top right there. Doesn't always sit on the floor. Typically, you're actually going to have it low wall mounted, maybe just above the baseboard. So a lot of different styles of air handlers. And up next, I've got a couple examples of what that might look like installed. So this is a trick picture because this is a horizontal ducted unit, which is hidden somewhere so you can't see it. All you're going to see is the grill on the wall, like a typical system you're used to. There's a picture of a ceiling recessed unit, sometimes called a ceiling cassette, mounted in a hard ceiling. So I don't see an access panel next to it, so I'm going to assume there's open attic above to access that for service. Here's, again, what I refer to as a floor-mounted unit, even though this one is not mounted on the floor. It's sitting, it's actually mounted on the wall just above the baseboard. And then the traditional high wall or wall-mounted ductless heat pump in that picture. We also have a ceiling suspended unit that's sometimes used in light commercial jobs, not often in residential, but just so you're aware of that one. Whether you believe it or not, we actually have some customers who don't like the look of the units hanging on their wall. I'm sure that doesn't apply to anybody in this room or on the webinar, but we have collected some pictures of some creative attempts to not necessarily hide them, but make them blend in to the decor. So I hope you'll appreciate these examples of that. If you happen to live in a log home, you can paint the unit brown so that it somewhat matches the wood, and I would argue that that blends in pretty well. Maybe they didn't match that wood exactly, but it's a nice attempt. Another option would be to conceal the unit in some kind of feature in the home, like a built-in bookshelf. This one, they definitely hit it. I'm not going to vouch for the performance of this unit. I'm gonna go out on a limb and say they probably did not calculate the net free area of that. So, and I hope it's removable or hinged so that we can get to that unit for service. So, I'm not recommending these, by the way. This might get the award for the most creative. Just like you can put a wrap on a vehicle, you can also put a wrap on a ductless heat pump. In this case, they wrapped it to look like books on a shelf, and that one is pretty well disguised, I would say. I hope those aren't their valuable first editions up next to it there, so that might not be such a good idea, but at least you can tell these shelves are removable, and certainly the books would be too, so we can get back to that unit for service. I think probably my favorite example of any of these, though, is what I would consider sort of integrated into the architecture in the building. So, this is obviously a built-in of some sort in the kitchen, but while it's not completely covered or hidden, let's assume that's the front door to the left. So when you walk in that front door, you have no idea that unit is on that wall. You literally have to go all the way into the room and turn completely around to see that it's there. So to me, that's pretty well hidden, but still very functional. I do have one other unit to tell you about. This is a brand new product that we just released this year that is a one-way ceiling cassette. So the 2x2 cassette that I described earlier is intended to go in the center of a room, usually in a commercial space again, but it blows out in 4 directions and then returns in the center. So it is intended to be in the center of the room. Whereas this unit is actually intended to be on the perimeter of the room. So it blows in one direction, kind of a sheet of air across the room, and then returns in the back side. It's also designed to go between 16 on center joists. So this is really easy, both in new construction and in retrofit. You're basically just cutting a hole and sliding the unit up in there. Functionally, actually, I'll show you a picture of the installation of that. You can see how it fits up between the joists. It installs sort of like a bathroom exhaust fan, I guess is the way I would describe it. The guts of the unit are up in the framing, and the only thing you see in the room is just the grill on the outside. And then this shows you that it does have a built-in condensate lift. We don't call it a pump, but it will lift condensate almost 20 inches, so that hopefully by that point you can reach a gravity drain. Gravity is your friend in this case, so we definitely like to rely on gravity to drain condensate whenever possible. Okay, so just to summarize some of the capabilities of residential VRF systems, absolutely high efficiency, energy savings. We talked a little bit about that already. Variable speed operation, and that goes for the compressor outdoors as well as the fan indoors. Again, being able to dial into what you define as comfort in each zone that we're able to create in the home. We're just trying to keep families together here and prevent fights over that the number on the magic box out there in the hallway. Quiet operation, that's something I haven't really addressed, but you literally cannot hear these things run. If we were all silent, you could just barely make out the air noise in here. So I would say, they did a pretty good job balancing this system. You don't hear a lot of the air movement here, but I don't know about your house, but at my house, when the big ducted system kicks on, I'm sitting on my couch close to the central return. I definitely hear that big whoosh of air that comes through that return. So with these low capacity VRF systems, they're running at typically such a low speed, you literally do not know they're on. So very quiet. Because we're always cycling air through the unit to sample the air temperature in the room, we're also running that through a filter. So you're getting literally almost constant air filtration as well. And everywhere you have an air handler, you're also filtering air in that location, as opposed to running it back through a central filter in your central return. And these units are definitely cold climate capable. So heat pumps have often gotten a bad rap that they don't work well in cold climates, but we have what is termed a cold climate heat pump, so that when it gets really cold, I'm in North Carolina, so I don't get maybe quite as cold as you do here, but the further north you go, the more you're going to need that low ambient heating capability out of your heat pump. So our hyperheat units will actually give you 100% capacity down to 5 degrees ambient, and you still get about 75–80% capacity at -13. I don't live here, but I'm assuming it doesn't get that cold here, not for very long anyway. So you can literally have your heat pump be your sole source of both heating and cooling in most climates in the United States without the need for backup heat or an auxiliary heat source. Just run through some quick application benefits here. Relatively easy to install. Takes a lot less time than building these big central duct systems. Indoor units that can be integrated into existing spaces. We looked at some examples of that. Room by room comfort, only providing heating or cooling where it's actually needed at that time. If there's a particular zone in your house that you're not using, you could literally just shut it off. Longer lifespan of the equipment, extremely durable. We talked about how quiet it is, and that goes for both the indoor units and the outdoor units. You literally cannot hear them run. Just want to tell you a quick story about a project in North Carolina, actually a little town called Cramerton that's near Charlotte. This is a development called the Villages at Cramerton Mills. It's a mixed-use development that includes single-family homes, apartments, office space, retail, restaurants, and a brewery. I don't know if you're aware of this, but you actually cannot build a development in North Carolina now that does not include a brewery. What's so funny? No, I'm not quite serious, but it's getting close to that. So all of the homes that are being built in this first phase of Cramerton Mills are certified to the DOE Zero Energy Ready Home program. This is not a requirement, but this developer chose to install a standard 3 kW PV array on the detached garage roofs behind the house, and then give buyers the option to upgrade to net zero by adding panels on the house roof. And if they choose the upgrade option, they also will throw in a 2-year lease on an electric vehicle and put a charging station in the detached garage. Pretty cool. So here's some of the features of these homes. 2x6 advanced framing. They've got zip system sheathing on the outside, dense packed cellulose insulation in the walls, advanced air sealing, low-E windows, and I suppose I will admit that my favorite feature is their cooling and heating strategy, which is probably why it appears in bold text there. But they like to brag that their systems are all 30+ SEER rated, so extremely efficient. Just to give you an example of one of the homes in Cramerton, this is the Dogwood plan. It's a 3-bedroom, 2.5 bath, a little over 2,000 square feet. For those of you who's familiar with the HERS score. Oh boy, maybe I should have put a slide in here on that. I may have assumed a little too much here, but essentially we're trying to grade the relative efficiency of this home as compared to a base home. So if you said that a typical code-built home was somewhere in the 85 to 100 range on this scale, a 0 would be a perfect score. A 0, in fact, would be a net zero energy home, a home that produces as much energy as it consumes over the course of a calendar year. Well, this home, because it has solar panels on it, it actually generates electricity on site. It is actually net positive. So it gets a negative score, which in this case is really good. So it's a -7 HERS score. I don't know if you can, you'll just barely be able to make out the condensers on the wall there at the back corner of the house. So they elected to go with all single zones in this case. So they're all 1-to-1s, 1 indoor unit per 1 outdoor unit. And that certainly maximizes the efficiency and the operating range of these systems. But it also means you have to locate 4 condensers, which we're going to have to wait till that landscaping matures a bit before we really are able to hide those. So a couple of interior shots for you here. You see the high wall, the mini splits as they're called, hanging on the wall, one in the great room and one in the formal dining room on the front of the house. So 2 heads, as they're sometimes called, on the first floor. On the second floor, the master bedroom got its own ductless heat pump on the wall there, and then there's also one out in the hallway that was sized to cover the other 2 bedrooms on that second floor. Yes?
Each of these have a corresponding exterior unit? Each of those sources?
That is correct. Yeah, so each of these are a 1-to-1, a single zone. So 1 indoor unit connected to 1 outdoor unit. We do have multi-zones as well. So, we certainly have an outdoor unit that's capable of handling all 4 of these. But in this case, he chose to go with single zones, again, for maximum SEER rating. We only have 2 units that are 30+ SEER, a 6,000 BTU, which is half a ton. That's our smallest. And then a 9,000 BTU. The 6,000 is 33 SEER. The 9,000 is 30 SEER. So those are the units that are used in these homes. What you cannot see is just around the corner in the hallway there is what we call a transfer fan. So it's essentially a bathroom exhaust fan, but rather than pull moisture out of a bathroom and dump it outdoors, we're pulling conditioned air out of that little short hallway and moving it into those 2 small bedrooms. The reason we did that is because the load is so low on those individual bedrooms. These are just little 10-by-10 rooms, and it's a high performance home. So the individual room loads are probably somewhere around 1,000 BTUs each. Well, we have the smallest ductless head in the industry at 6,000 BTUs, but that's still grossly oversized for a small bedroom. So what we chose to do is size this head for the load on that hallway. There's actually a hall bath and those 2 bedrooms, and combined, this has enough capacity for all those rooms. And then we used the transfer fan idea to move air into those spaces when there's door closure for privacy. When the bedroom doors remain open, everything, flows naturally, and it works out great. So that's the end of my section, I believe. No, we're not taking questions till the end, correct?
At the end.
Okay. You're up.
All right. Again, my name's Nikki Kruger, and I'm with the company's called Thermistore, and we manufacture the Ultra Air whole house ventilating dehumidifiers, and most recently in-wall dehumidifier, which we'll get into a little bit. There we go. So there is a software program out there called BOPT, and you are able to go into the software and put in your location, and you can pick a specific code-built house. So we've got a 2015 IECC code-built home here in Arlington, Virginia. And whoops, let's go back one. What this is showing me on this slide, I'm going to wander too, I need to stay, is we have about 8,765-ish hours in the year. I asked Siri, I forgot what she said exactly, but it's around there. And what this slide is showing us is we've got a VRF system, a multi-stage system, a 2-stage system, and a 1-stage heating and cooling system. And if you see over there on your left-hand side, that's the RH. So if we go up to that 50, I need a clicker here, a pointer, a 50% RH, Vanna, stand up, there we go. There's going to be about 5,000 hours in that year where these systems are not going to be able to keep that space or that building or home below or at or below 50% RH. So the goal of right-sizing our equipment and getting the equipment sized for the smaller loads, which is more square footage but less ton, is to try to at least get our HVAC equipment set up to move that as down as much as possible. So with Rob's equipment, hopefully we can adjust that, get them right sized. But the reality is, if I added a 1-stage system with a dedicated dehumidifier, I could keep that at 50% RH and not have to count on that HVAC system to always control my RH. Let the HVAC system run, remove water when it's running, but right size it, and then have the backup system of dehumidification to always keep the relative humidity in check. And we're going to go into a little bit more why that is, and really the need for dehumidification is significant. It's our health, it's our comfort, it's our belongings, and it's the structure of the home. Moisture is the #1 detriment to any building. Obviously, if there's bulk water leaks, anything like that, we've got to address that. But by reducing our loads on these high performance homes, we're now taking away our drying mechanism, and it's not running as long. So we have lots of organizations out there that have different recommended relative humidities. American Lung, American Medical, 50%. ASHRAE's keep it less than 60. Building Science Corp, 25 would be wintertime, 60 would be your max in the summertime. And here's an ASHRAE chart that a lot of people use, and it's out there. But again, that optimum zone is 30 in the wintertime, and your max is 60, and really you want to be around, we typically say 50 to 55% relative humidity in the living space. So there are a lot of dehumidification strategies that are being implemented right now, and basically it's trying to use the system that we already are putting in the house in order to dehumidify. So if we look at our air conditioning and single stage, but There are thermostats out there that have relative humidity on them, but really you're overcooling to dehumidify. So again, the thermostat, we all have homeowners, we're all guilty, we're uncomfortable, we go over to the thermostat, we start cranking it down. We're overcooling to dehumidify. And one of the challenges we've always said is, well, that doesn't solve 70 and raining. So this morning, you didn't need air conditioning, but it was so humid. The reality is 70 and rating is a lot of times now our high performance homes. It's no load to low load buildings where our air conditioning just isn't running as much. And we've got to bring in that fresh air. And we shouldn't be building our ventilation strategy worrying about the conditions outside. If people live in a building, they need fresh air. And we can't block out certain times of when they need that fresh air. We need to add the system components to make sure that we've had comfortable, healthy homes and not eliminate anything based on what's going on outside. So one-time AC provides, and this is basically your single stage kind of standard equipment, but usually that's about 10,000 BTUs of sensible cooling and 2,000 BTUs of latent. The reality is in our high performance homes, our needs are changing. We need about 2,000 BTUs of sensible and possibly up to 10,000 of latent to get that water removed out of those buildings. So what's important to remember with our AC systems is when that AC comes on, it's not instantly removing water. It can take up to, and there's a chart here, about 14 minutes of runtime for those coils on that air conditioning system to load, to get saturated, and water to start dripping down the drain. So when we're looking at using, the equipment, the VRF equipment that's doing the single zones and the smaller rooms, the reason we're using those is because they are so energy efficient. But the reality is we're not getting the runtime on that equipment in order to get the water out of those spaces. So again, as we started out with, no good deed goes unpunished. I mean, the goal is to be energy efficient, but now we've kind of created another situation. So variable speed slows the air conditioner fan down, makes a smaller amount of really cold air, and it can create some really cold surfaces. So that duct work now could even be colder, which means we've got to start worrying about dew point issues, and possibly if it's not insulated correctly, or if we're getting some infiltration from the outside where that ductwork is, we've got a greater condensation issue. Registers like this, typically you see that in Florida quite a bit. The metal registers, they're getting cold, they're getting condensation on them. And again, we always tell, well, I work with a lot of HVAC contractors and they'll say, oh, I got it. We use variable speed. That dehumidifies. Well, one speed of variable speed is off. And so when that homeowner walks by and it's 70 and raining and there's cold air coming out, they're probably going to shut the system off. So ductless mini splits, again, really great for creating the right comfort, can cool space very quickly. I wouldn't count on the dehumidification mode. Dehumidification mode, again, is putting it more on a timer system, and it's creating cold spaces in order to try to control that humidity. One thing that Rob talked about is SEER, and SEER is really the rating of how energy efficient that equipment is. So we've made some changes in our equipment in order to get these higher SEER numbers. They're typically larger coils that don't get quite as cold as they used to, and they can hold about a pint or a pound of water. If you're not familiar, a pint's a pound the world around. So anytime you hear somebody talk about a pint or a pound of water, it's the exact same thing. But those coils hold about a pint of water. As I said, they don't get quite as cold as the old coils used to. And one of the ways that they get their higher energy efficiency is they run the fan 1 to 3 minutes after the compressor shuts off. So all that pint or pound of water that's on that coil, actually gets re-evaporated back into the air, and you can increase the relative humidity by 10%. So no good deed goes unpunished. We're energy efficient, but we're contributing to moisture issues. Rob mentioned the sensible heat ratio. The sensible heat ratio is basically how much water that air conditioner is going to take out. And what I want to point out here is it usually goes, you can see here by the SEER. The higher the SEER, usually the less amount of water that system can remove. So I'm not sure if anybody is monitoring those homes in North Carolina. I'm sure they are being monitored, but those 30 SEER systems do not have very good water removal at all. So not sure if MD33s are in their future or not. So best practices. We talked about load calculations. This is how this happens here. Contractor is going to size that equipment for the peak loads of the year. So weak in summertime. I think this one is based on Texas. So the cooling design load is 93 degrees. We're going to size that system based on 93 degrees because we don't want on the 4th of July when there's 20 people in our house to be uncomfortable and to get a call back. So we're going to size that system for the worst case scenario. Then we're going to add how many people are in the house. We got 4 people. And then how much fresh air are we required to bring in by our building standard or our certification that we're trying to meet. And then that's going to give us our total cooling load, our sensible load, and our latent load. Again, our sensible load is 29,000 BTUs, and our latent is 7. Well, we know the sensible load throughout the day of a house is going to variable. It's going to be cooler. You're not going to need the air conditioning in the morning. You're going to need it afternoon and then throughout the day. The challenge with the latent load is you can be at, today, a 75-degree dew point, which is extremely uncomfortable throughout the entire day. But your systems aren't sized for that. So those two numbers are probably getting more and more in these high-performance buildings and homes that the sensible and latent loads numbers are reversing. Our sensible loads are low, our latent loads are high. So we've got a case study here. This is actually in a multifamily building in Fredericksburg. Again, doesn't matter if it's a multifamily apartment or if it's a single family home. It was constructed in 2015, and the apartments ranged from about 600 square feet to I'd say about 800 square feet. And they put in 2-stage equipment for each of the units because they wanted to use the 2-stage to dehumidify. 2 years, last summer we went in and there was several apartments that were having significant mold issues. And what was going on was the tenants were uncomfortable. And so in this particular apartment here, she just kept cranking down the thermostat. So you can see up there, when we went in, it was 66 degrees in her apartment with almost a 75% relative humidity. This is what the walls looked like in this apartment. So they had to move them out. They had to remediate. What we actually ended up doing is installing a new in-wall dehumidifier that will fit into a 2x6 stud wall or a 2x4 stud wall, 16 inches on center. And we were able then to put that in after all the remediation was done and keep it at 50% relative humidity. And as you can see where that red line is up there, that's 75 degrees. The tenant could put their thermostat back up to a comfortable temperature, and we had a comfortable relative humidity in these apartments. We've done one whole building, and then as of this week, there's 2 other buildings that they're going to be doing there as well. So one way that you can figure out how much dehumidification you are going to need is we have an app. It's free. You go into your app store, and basically, I'm going to show you an example of how to use this app. So we've got 70 degrees outside 100% relative humidity, and a 70-degree dew point. So what I can do is on the inlet, the inlet means that's our outdoor conditions, because that's what we're looking at, the fresh air that we're bringing in. That's our conditions of outside. So 70 degrees and 100% relative humidity. And in the house, we want 70 degrees and 50% relative humidity. We're not running our AC system, which again could be very typical in our high performance homes, not running our low loads. And I know that I've got to, based on my calculations for ventilation, I need to bring in 100 CFM of fresh air. So one way or another, if it's not a tight home, you're getting infiltration of probably 100 CFM at least. But based on our ventilation alone, this is telling me that I'm going to need 91 pints a day of dehumidification in that house. 70 and raining. Is my AC running very much? Probably not. So the challenge with this, especially when we have summers like we've had, where we're not drying, we have constant wet outside, is we're not getting enough drying potentials in our homes to always address that amount of moisture that we need to remove. Again, that's a free app. If you need more info, let me know. So we talk about ventilation and using that app. It's very common in a lot of these certifications and standards for high performance to require an ERV. So basically some sort of balanced ventilation where we can get an exchange of energy to pre-cool or preheat that air. And then an ERV has a latent exchange. So based on how humid it is outside and how humid it is inside, when that air balances and goes through that core, there'll be an exchange of that moisture. It can reduce the moisture 30 to 50% in that air, but it will always still, when it's humid out, contribute to the moisture load in that house. There is no set RH on an ERV, and ERVs don't have drains to remove moisture. If they have a drain, it's usually an HRV, and that's because the core will freeze and it's got to defrost. So when it comes to ERVs, don't let someone tell you that it's a dehumidifier. It will take out some of that moisture from the outside, but again, if it's humid inside and humid outside, it's all kind of Russian roulette on exactly how much exchange you're going to get from that core. So I've got a case study here, and the case studies that I'm talking about, I had them out there if you want to pick them up, but this is a Orlando home. It is a NHB emerald green home, and the homeowner at the time, this was a show home for the International Builders Show, really wanted to put in our equipment, but there was a significant manufacturer of the equipment that was donating it to the house who said, no, we want to put in our ERVs. So we said to the homeowner, that's fine. Why don't you do that? Once you get the home back, then we can start putting in the dehumidification equipment. So what we did is we monitored, and we did partial loads for monitoring, because again, most of our homes are now running in partial loads and not at peak loads. So over here on the right, you can see that the RH line is the blue line, the green line is the outside dew point, and the red line is the outside temp. And basically our relative humidity in the house is following the dew point line outside. This homeowner did have some health issues and had to use oxygen. And so the interior moisture issues being high for him was even more problematic because of the condensation in the mass. So what we did is we took out the ERV and we used our dehumidifier to bring in the fresh air and then also dehumidify the entire home, independent of the AC. And basically what you can see there is we set it at 55%. We don't care what's going on outside. We just set it, and when it needs to come on, it comes on. Now, the ideal way to set up these systems when you're using some form of dedicated dehumidification is to set up the AC to run at its best performance, hopefully longer periods of time if you need it, and remove as much moisture as possible. And then when that shuts off, then the dehumidifier, if it's above your set point of like 55%, then the dehumidifier comes on. Now that's the most energy efficient way to do it. We've had homeowners that say, I don't care if the AC is running or not. If it gets above that threshold of 55%, just have the dehumidifier come on and they'll both run at the same time. But that is really the most energy efficient way to set these up. All right, so Armin Rudd, he is definitely an expert in moisture, and he did a study for the DOE on ERVs, and basically what he said is the ERV is ineffective in keeping indoor RH down during floating hours, when the difference between the indoor and outdoor absolute humidity is small. So our floating hours, we've always typically said, are spring and fall, and then the mornings and nighttime, again, when our AC is not running as much, but there's also not a lot of difference in the humidity inside our home and outside our homes. So in conclusion, we want to make sure our envelopes are tight. We want our buildings as tight and as energy efficient as possible. We need to right now use Manual J to size our equipment appropriately. I will tell you that there is a new committee that I'm involved with and sitting on. It's a new manual by ACA. It's called Manual LLH, which is low load homes. And it will start the sizing of the equipment at 1,500 square feet per ton. So it's going to be pretty aggressive, but it's the reality of what we're seeing in these high performance homes. But right now, Manual J is the resource for sizing our equipment. You got to bring in the outdoor air. You got to bring in that outdoor air to meet ASHRAE or any other standard. And we need to add dedicated dehumidification. We've got our heating, we've got our ventilating, we've got our air conditioning. We can't count on the air conditioning to do our dehumidification anymore. We've got to add that D to the end of it. And I think that's all I have. If you have any questions, I think. Okay. Oh, and my word is Ovaltine.
There you go. So again, for those of you on the webinar, if you want your AIA credits, we'll be giving out a poll here in a few minutes. You'll just answer the question with the 3 words that our speakers gave, and there'll be a multiple choice question. So you'll give us the phrase to be eligible to get those credits. As a reminder, we will be sending out the slides to everyone. So you'll get an evaluation email from us today. Slides may come a little later once I can regroup with these guys and get those out to you. If you are interested in AIA credits from the webinar side, just reply to that email directly with your name, your AIA number, and if you want a certificate or not. And we will get that issued as long as you get the question right that we're about to give you. And we'll be taking questions now. We still got about 30 minutes. Hang with us on the webinar. If there's a question in the room, if you can't hear it for a second, we will have the speaker reiterate it so you can hear it. But I'll let you go ahead, and if there's questions from the room, I'll also issue the poll right now, but I'll let you go ahead and take a question.
All right. Anybody?
And thank you so much to you guys, to Nikki, Rob, and Chris. Great job, guys. Thank you.
Yes?
Thanks for letting me ask a question. Christy, this is kind of a two-person question for both of you, I think. This has been the summer of love for me when it comes to duck sweat. Seen more of it this summer than I have ever seen in my entire career. And it's the only thing I've noticed for sure is it's not duct systems I designed. It's retrofit systems we put in on existing duct systems. Usually all the other factors in play are pretty normal. Ductwork in conditioned space, but oftentimes in bulkheads that's connected to band joists, things like that. I'd come in and run blower door tests. I hadn't found the leakiness of the house to be really ascribable to it. My go-to solution has been insulating this ductwork, even though it's in conditioned space. I thought dehumidifiers possibly as a solution, but then again, if it's inside of a bulkhead, drywall, that's in the pressure boundary. Outside the pressure boundary is a dehumidifier problem.
Who's recapping
I guess the question I have is, what is the best solution or best
Sweaty ducks.
Yeah, can you
make
recap?
these problems go away? Oh, and it's all obviously variable speed systems. I'm pretty sure that the technology is displayed in the sense of supply air temperature being extremely low.
Good old sweaty ducks. Yes. So in basically all low load homes that we're working in now, ducts need to be insulated. Multifamily, single family, light commercial, they've been doing it forever.
Even if it's in conditions.
Even in conditioned space. Yeah. And kind of what this whole presentation was is that we're not able to remove the moisture like we were. So we're starting to creep up a little bit on our relative humidities in the house on a more consistent basis. And our ducts are 55 degrees in there. You know, it's coming off the air handler at 45. It's 55 in the ductwork. So you can run through that sweet app that Nikki showed, where you can run through different conditions and show where your dew points are less than 55. What's happening is we're often above 55 dew point. And if there is warm, moist air just kind of lingering in those rimming bands or in those bulkheads, it's going to start to drip. It's going to condensate and start dripping. The best two ways to deal with leaky ductwork is insulate them from the get-go, and then control the relative humidity of the house so you don't even get near the dew point of 55.
So control the relative humidity with a dehumidifier, even though that's in the envelope, it's going to contribute to the process you were talking about drying out materials.
Yes, it will. It will. Huh?
Just recap what you said.
Oh, go ahead and ask again so I can repeat it.
Adding dehumidification inside the envelope is going to contribute to the process you were talking about with drying out the materials.
Yes, so adding dehumidification will add to the process of stopping or preventing the ductwork from condensating. Your first line of defense is absolutely going to be insulating them. And really, it's not about the insulation. It's about creating an air barrier from the warm, humid air into the space to the ductwork. So the insulation, quite honestly, often has very little to do with it. It's just stopping the air from touching the ductwork. But if that air that's touching the ductwork is not laden with a bunch of moisture, it's not going to condensate. It'll just kind of wash over it and be good. So absolutely, first and foremost, insulate your ductwork and have, at a minimum, a spot or a design strategy to include a dehumidifier if you have to, right? So it's always easier to design a space up front, plug and basically a drain. So, yeah.
Great, thank you. I'm going to close the poll now, last chance. And I know we do have one question coming in on the webinar. I'm going to let Mannion come up and present that question.
Okay. We actually have a couple questions from folks on the webinar. So the first one is, are there any studies or data that we can point to that confirm airtight construction actually reduces latent cooling load? Anecdotally, it seems like we see more latent load issues in our tighter homes. How can we combat this common misconception? You're welcome to come and read it.
Really good on the question.
Yep.
Sounds like a Jones Sounds like.
Yeah, so are there studies or data we can point to that confirm airtight construction actually reduces latent cooling loads? I am not aware of any in a hot, humid, or mixed humid climate that it would show it reducing the latent load. We probably had infiltration of that air coming in at some point. But usually when our houses were leakier, we would wet and dry. Now our airtight construction and having to bring in the fresh air, and then of course adding our people, we're trapping in a lot of that moisture into the building. So I think there's probably a lot of studies showing that we're lowering our sensible loads for sure, but I am not aware. Most of the data that I have and that I've seen shows we're increasing our latent loads. And I can tell you what, after this year, this summer and fall so far, the latent loads are high in a lot of buildings and homes. We've had more calls and sweaty ducts. I mean, everybody's, can I add a dehumidifier? And I'd like to tell you that just adding a dehumidifier is going to solve that, but it's not. I mean, they've got infiltration issues somewhere or something going on with the leaky, the ductwork that needs to be fixed first, and then you can add a dehumidifier to it.
Was there more to that question? I think that pretty much covered that one.
Okay.
And then we have another one. This one's for Mitsubishi. Is Mitsubishi developing an ultra-low capacity indoor units to allow right sizing in high-performance homes? Most ductless units currently have too much capacity for single zones in tight houses.
I'm not at liberty to say. Okay, I guess I am. Yes, we are looking at designing a smaller capacity unit that I would call basically a bedroom unit that would be somewhere closer to the 3,000 BTU range. When that would actually be available, I have no idea, but it is definitely something on the drawing board, and we know it's certainly needed in the industry.
And what is the MERV rating of built-in Mitsubishi ductless filters?
I'd like to know who's asking these questions, please. To be honest, I don't know the exact answer to that question. Anecdotally, I've been told that it's somewhere around MERV 6, but it's certainly not the level of filtration that you need. In other words, what is recommended by the Department of Energy and the national labs who do research on indoor air quality. Filtration is something else that we're definitely looking at, trying to find a way to improve.
So
you want to hit that one?
Speaking of filtration, the ultra air dehumidifiers, because you can use them to actually bring in fresh air to meet your ventilation standard, all include a MERV 13 filter, which is an extremely effective filter. And also what that does is when you're dehumidifying your house as well, it's also will be bringing in that air through that unit and filtering the air from the house when it's going through the dehumidifier as well.
Any other questions?
Yeah, I have a couple. One for you. Are these ultra air ventilating dehumidifiers set up or installed similarly tied into a HVAC system like an ERV would be?
So the question is, are the ultra air dehumidifiers tied into an HVAC system similar to an ERV? So most ERVs typically have their own ductwork a lot of the times, at least they're recommended to. So when you install an ultra air, and we have several install options based on what you walk into, but our recommended is to have a dedicated return to the dehumidifier. So if you can pull from a common living space, the living room, and then we use the supply ductwork of the HVAC system to distribute that dry air. So by setting it up that way, you don't ever have to use the fan on the HVAC system to move the air through the ductwork. So it's the most energy efficient way. So basically, all we really want is that supply ductwork in order to distribute that air, and if you're bringing in fresh air throughout the entire house. So you don't have to use our dehumidifiers to bring in the fresh air. If you're using an ERV, you can not use the fresh air duct if it has one. Our smallest unit is the only that doesn't have a fresh air duct. You just have to tie into the return of it. But you can just set it up to dehumidify the entire house and not use it for the fresh air.
See, we do a lot of, we tighten up the houses. So we're dropping infiltration rate considerably. So we get down to the ASHRAE standards where you need mechanical ventilation to improve indoor air quality. And so it's really in a retrofit scenario. So we're ultimately tying in, we're drawing air out of the returns, and we're conditioning it. We're bringing in new air through ERV and pumping it into the supply side. But I'm looking at options where we're seeing tighter houses, and we need that fresh air for indoor air quality, but we also need the dehumidification because we're getting them tighter and we're not getting the system run times. Very similar to new construction, but we're working on the retrofit side.
Yep. So in retrofit, you're always going to run it. I mean, a dedicated return is not always easy in retrofit. So we have the return, you can pull from the return and dump in the supply. You might just need a check damper so we're not getting, just circulating the air through the system. Or you'll have to run the fan on the HVAC system when the dehumidifier is on. And that just stops the air from kind of circulating like this through it. But we have lots of install options available. And again, we are a positive pressure ventilation system. We're supply. So they're typically in a lot of homes where we want in humid climates more of that positive pressure in order to stop the hot going to cold and the wet going to dry. You got your bath fans, you got your kitchen hoods, you got your dryer. There's a lot of negative going on in the house. So we try to help that out a little bit by being that supply. But again, if you're using an ERV, just set us up to do dehumidification.
Well, yeah, we have to obviously worry about the balance in the homes too, because we're often trying to control humidity, because I have yet to, probably once in 10 years, seen a bath fan that's sized right and installed right. So,
yes.
So we often are doing bath ventilation, kitchen ventilation, often for indoor quality, but then we have to worry about the combustion side of things if there's natural draft equipment in the house,
yep.
So potential backdrafting. So we're always looking at all those factors and balancing the home. So.
Sure. And I just want to say real quick, Rob and I do a lot of presentations together, and we work with their high performance team with their ductless mini splits. So we've run into, when I showed that apartment, that case study, and I said the MD33 dehumidifier, that is that in-wall dehumidifier. So if you don't have ductwork and you need that dedicated dehumidification, that unit can just, go on the wall and help treat that space. And we say up to 1,200 square feet for that unit. But again, if everybody's keeping their bedroom doors closed and you've got a lot of a compartmentalization, we might have to figure out something else. But our dehumidifiers can have its own ductwork too. So it's very simple ductwork. You don't need a lot of it. But that's an option too when we're integrating. We've done a lot of projects together that have worked out very well. There was a question back there. Go ahead. Yep. You. Yeah.
When I'm in the home, where we have the basement, first and second, what about using the mini split on the basement to kind of address the problem that we mentioned before that we have on our basement? And then with the one equipment for the first floor, that usually it is located on the basement, and then it will be another equipment on the attic for the second floor.
Mm-hmm.
So if that is the layout, how did you handle the dehumidifier? It would be for the attic unit, another dehumidifier for the first floor unit that is on the basement, and then the split unit?
So the question is, when we're talking about different level homes, someone had mentioned earlier that they've got humidity or comfort issues in their basement. And so could we use a mini split to treat the basement and then for the other levels have a ducted system? And if we did that, how would we address the dehumidification? So I would say that if you're using the dehumidifier for your fresh air and for dehumidification, you would put one on that system to address the square footages. So let's say you've got 1,800 square feet. Then you could use our smallest dehumidifier to do that. And then basements are tricky. Basements, the humidity is always typically going to be higher because you have cooler. Now, what's good is you could use, we also manufacture basement and crawl space dehumidifiers that could go in that space. If it's a finished space, you could use our in-wall dehumidifier. But I mean, I just was on a call with a guy in New York yesterday who's got these high performance homes that are having a lot of humidity issues. And he's got an apartment in the basement, and then he's got a finished space in the basement that it's a Pilates room, and then he's got upstairs.
Sweaty goat yoga.
Yeah. So he's going to put an MD33 in the apartment. We got to deal with that space. And then we're going to put a dehumidifier on the rest of the system, because he does have some supply ducts that go into the basement. And so if we push some dehumidified air down there, then we'll see what happens, because it's a big open stairwell from the basement to the first floor. So as long as we have communication between the areas, then I think that's going to work. Now, one of these houses is his own home, so he's a builder, so he's going to try it. It all depends on how much water vapor we're getting in that basement, if we're going to have an actual dedicated dehumidification for not the apartment, but that other space. Because relative humidity is typically, it's cooler down there, and the heat from a dehumidifier in that space usually is a good thing, a little bit of heat. So it works out well. But yeah, sometimes you got to look at where your systems are and then how you're going to integrate with them.
Especially if you have a renter.
A renter is a big one. Yep.
You have to manage the level of humidity and the temperature. Then we cannot use the same unit, which was the standard of 1 unit for the first floor and the basement. Because then the thermostat on the first floor is going to be okay, but the renter is going to.
And that's why I would.
Yep. You will make it work more, which is the problem that we are having.
Well, the control for the dehumidifier typically is going to be located next to the thermostat, or it could be the thermostat, because we can tie into some thermostats that have the RH and ventilation. So, but ours gives you a little bit more capability. But again, that's going to be in the central living space typically, is where it's sensing the relative humidity. So if you've got a basement apartment, I would say that you would probably need that in-wall that's it's sensing the RH in that area in dehumidifying to that specific 55%.
So we can have 1 unit for the first floor and the basement, with the equipment on the basement, but maybe with 2 zones.
We can talk about this. Yeah, we've got options for different duct work and stuff like that. We can talk about that. Yeah.
Yeah. Let's see if we got any others. This one was asking if Mitsubishi provides MERV 13 upgrade filters for ductless units.
No, not for ductless units, but you could certainly use those on our ducted air handlers.
And then, do you have a recommendation for the best smart thermostat?
I don't. Do you, Chris, have a recommendation for the best smart thermostat?
They all operate basically the same.
It all depends on what key features you're looking for.
And how you integrate that into all these, different pieces of equipment that we're talking about. So to me, it's picking one that has the ability to communicate with the heating and cooling and ventilation strategy. But yeah.
The problem with them all, if you want to say it, the problem with them all, they don't work with multi-speed systems. Right? They're not good at variable speeds. It's on or off. S is on or off.
Yeah. So, Chris was just saying that they don't tend to work very well with VRF or multi-stage equipment. They're really designed more for single stage.
Yeah, go ahead.
For a gentleman here, you talked about single head systems being too big for a particular room. You gave an example if I put it in the hallway, and we use fan strategies to move the air around. Can you talk a little bit more about that? Because I'm not familiar with those fan strategies and how you actually incorporate that?
Sure. So the question was, could I give more detail about the example I used where we were using transfer fans to move conditioned air into bedrooms? Yeah. So, this is something that we're, still doing research on in partnership with Department of Energy and a lot of the different research labs around the country. So it's certainly not an exact science at this point, but, it's a simple idea. It's just, we're still trying to monitor these projects to see how effective it is. And I would say we've had mixed results, to date. But this specific project I'm referring to, we've not had any comfort complaints, from these homes. But yeah, in essence, you're just taking the conditioned air out of that hallway, so we're in essence.
Concept, implementation, I didn't understand how that was really implemented.
So there's a couple different products out there that we've tried. Some of them are wall-mounted bathroom exhaust fans. So you're literally just taking air from one side of the wall and transferring it to the other side. And I like that strategy because you're keeping everything inside conditioned space. We've also seen some attempts to mount a fan in the ceiling or even a remote mounted fan in the attic so that you're, basically pulling air out of the hallway and then dumping it into the bedrooms overhead. I would say that if you go outside of the envelope, outside of conditioned space, especially through a hot attic in the summertime or even a cold attic in the wintertime, that has not been very effective. So yeah, I would say if you're going to try that approach, you definitely want to try to keep everything inside conditioned space.
You can actually use thermostatically controlled air transfer fan as well, so there's thermostat in the room that activates it.
Oh, really? I've not seen that.
That's what I've done that before. I've had really good luck.
Yeah, the comment in the room was that there are some transfer fans out there on the market that are thermostatically controlled, and I can certainly provide some links to those products if you like.
Sweet. All right on time, everyone. Thanks for hanging with us through the Q&A. If you have any other questions, I'm sure you guys could hang out for a few minutes in the room here. But thank you so much to all of our speakers, Rob, Nikki, and Chris. That was wonderful. Thanks to Helen for her help with Arlington County setting this up, and the library, obviously, for hosting us. And thank you all for being here on the webinar and in person. And hopefully you'll join us for a future event. So have a great afternoon. Thanks.